Hey everyone, it's Mrs. Cook. Welcome to section 1.5, which is called Infinite Limits. And what I'd actually like you to start by doing is this warm-up here. So pause the video, work through the warm-up, and then we'll come back and we'll see if we agree on the answers. I'm serious here, everybody. Pause the video. I went ahead and I simplified the function that was given to me. I found that I had a hole located at -2, -4, and a vertical asymptote located at -2. I used a table of values to go ahead then and graph. Here I went ahead and graphed my branches. I noticed that I had that hole right there. So when I described the discontinuity, I said it's discontinuous right here at this hole that I had graphed right there. And then it's discontinuous also, of course, at that vertical asymptote. So when I was calculating limits, then look what happened. Here, as I was calculating my limits, I noticed that the limit at -2 is actually -1/4 because from the left and from the right, we're approaching that -1/4. But the limit at a +2 does not exist because from the left we were approaching -infinity and from the right we were approaching +infinity. So these are some of the ideas we're going to be talking about here with our topic of infinite limits. Let's take a look at the learning target. So we are going to evaluate limits approaching infinity. And there's a little review here for you. A hole is called a removable discontinuity. So go ahead and write that in there. And excuse my handwriting on this tablet. Now notice as we approach a hole from the left and the right, we actually got a number for the limit that happened right here as evidenced in the warm-up. A vertical asymptote though is called a non-removable discontinuity. And as we approach that vertical asymptote, you'll notice that in this case, we got does not exist. Now, sometimes we'll get does not exist, but if they both from the left and the right had approached the same sign infinity, then we would have gotten either positive infinity as an option or negative infinity as an option. So watch for those options. We're going to take a look at the 4 options actually that we're going to see when we plug in this value of c here into a function. So one option is going to be that we get 0 over a number. If I get 0 over a number, well, 0 divided by anything, that's going to tell me that the limit is going to equal the number 0. How about if I get 0 in the denominator? If I plug in that value of c into a function, I get a number on the top and a 0 on the denominator. That is going to tell me that the limit is going to actually equal either positive or negative infinity, and we'll take a look at the signs as we do that in the next page. 0 over 0, we've been talking about this. This guy is called indeterminate. And what we have to do is that plug, play, plug idea, where we plug in the value, we end up getting 0 over 0. We say, no worries, we're going to play with it. And that's when in the warm-up, you can see that I went ahead and I played and I reduced my function right there. And then I was able to plug in and figure out what the limit was. So when I did that, I ended up getting a number as the final answer. And if I just get a number over a number, this is my very favorite kind of limit because that's the quick kind that we had on some of the quiz where we just plugged in, we got a number over a number, and we simplified that number, and we ended up saying that that number was the answer. Okay, so these are the 4 options that we're about to see. Let's take a look. I find each one-side limit algebraically, meaning I don't have a graphing calculator. So I'm going to do the first step, which is to plug. And when I plug, I'm upset because I'm going to get 0 in the denominator. But when I do get 1 over 0, that is telling me my options. And my options when I get a number over a 0 are either going to be a positive or a negative infinity. How do I figure out which one it is? Well, notice this is telling me to approach 1 from the left. So if I approach 1 from the left, what I'm going to do is plug in a number almost there. So like maybe a 0.9. And if I do that, if I plug in a 0.9, I will see that in the numerator, I get a positive number, and in the denominator, you'll see I get a negative number. That's all I need to determine that my limit is going to actually be negative infinity. So it's not even that we care about what number we get, it's that we care about the signs of the number that we get. So take a look at the next one. If I plug in a 1, I'm in some trouble here because I'm going to get that number in the top and that 0 on the bottom again. Again, that communicates to me that I'm going to have either positive or negative infinity. And so to figure out which one, let's plug in a number that's approaching 1 from the left-hand side. Again, if this is my number line 1, let's approach it from the left. So let's plug in something that's very, very close, like a 0.9. If I do that in this case, I'm going to have a 0.9 squared minus a 3 times 0.9, and then divided by 0.9 minus 1. If this is too overwhelming for you, you definitely could have factored that numerator and had an x times x minus 3, in which case you're thinking, okay, it's a positive number times 0.9 minus 3, which is a negative number. Remember, the only thing we care about is the sign of the numerator. So we're going to get a negative number in the numerator, and in the denominator, in this case, I'm also going to get a negative number. And that means that my limit is going to be a positive infinity in this case. All right, example 3, here we go. We're going to plug in that 1. We're going to be in some trouble because we're going to get a number over a 0 again. So again, I know I've got a 50-50 shot here. I'm going to this time plug in a number that's approaching 1, but from the right-hand side. So I want to plug in a number that's just over 1. Let's go with 1.1. When I do that, I get 2 plus 1.1 over 1 minus 1.1. Again, don't even worry about what number this is. Just worry about the sign of it. This is going to be a positive number over a negative number, and therefore I'm going to be approaching negative infinity. Going and got signs, example 4 is super refreshing. Take a look. If I plug in a 4 this time, I get 4 squared over 4 squared plus 16. I don't run into any trouble whatsoever. I get 16 over 16 plus 16, or 32, and my limit is a 1/2. That's this case here, where when I plugged in, I just ended up getting a number over a number. My very favorite examples because they're nice and quick. But then we get to this one, and if I were to plug in a 4, I'm in some trouble. In fact, here I'm going to get 0 over 0, which is indeterminate. So that tells me I need to do a little bit more. We're going to play with it by doing some factoring. And when we do that, we'll notice, oh, look, we have a hole located here at, when x is 4, at 1/8. So I'm going to determine that hole, and then I can plug in that 4, and that's how I knew that the limit was at 1/8. This one is the indeterminate example. Just to show you, we're always going to get one of 4 of these. That was this example here, where I plug, play, plug. And finally, in the last one, I'm going to plug in a 2. I'm going to be in some trouble, but this time I'm going to get 4 over 0. So that's this last case here, where I got a positive or negative infinity once again. And to determine which one it is, I'm going to plug in a number that approaches 2, but this time from the right. So let's go with 2.1. I'm not worried what 2.1 plus 2 is. I know you guys can calculate that, but what I'm actually concerned about is what is the sign of that. So this guy is going to be a positive over, well, 2 squared is 4, so 2.1 squared is bigger than 4, and 4 minus 4 is going to be a positive number. If you don't like that, then by all means, just go ahead and factor this x plus 2, x minus 2, and then plug your 2.1 in there. So you certainly can do it that way to say, oh, I would have a positive here and a positive here, and end up with a positive infinity, or just infinity.